Hi, welcome back. This video is on Coulombs Law and point charges. Coulombs Law forms the basis for electricity and electric fields, so let us check it out. Now, what you have to understand is that Coulombs Law cannot be derived. It's an experimental law, and it says the following. I'm just going to write it down. Your life will never be the same. Okay, the force. I'm going to say force, and I'm going to give it subscripts 1, 2. Force is a vector. Equals K Q1 Q2 over R squared times a unit vector, which I'll give subscript R12, like this. So this is Coulomb's law for point charges. So in this equation, Q1 and Q2 are so-called point charges. Q1, Q2, point charges. And remember, charge is measured in coulombs. So Q1 is coulombs, Q2 is coulombs. A point charge means that it's a charged body. We usually draw it as like a circle, a filled-in circle, whose dimensions are so small compared to all the other dimensions that we can just consider all of the charge existing at a point. All right, that's a point charge. In this equation, R is the separating distance between those point charges. R12, okay, this, you see it come up in the subscript. R12 is a distance vector. Distance vector from charge 1 to charge 2. Getting that order is important. So you see I'm underlining from and to there. F12, so let me back up. So A subscript R12 would be a unit vector in this direction. F12 is the electric force on, and getting that is crucial, on Q2 by Q1. So we haven't talked about K yet, but what this is saying is that electric force is proportional to Q1, it's proportional to Q2, it's proportional to, or inversely proportional to the separating distance squared, and the constant of proportionality, K, is approximately 9 times 10 to the 9th meters per farad. It's approximately that. Okay, but we'll often break this constant down into a different constant, 1 over 4 pi epsilon 0, like this, where epsilon 0 is exactly, not exactly, but up to 4 significant digits, 8.854 times 10 to the minus 12 farads per meter. And you say, well, why do we do that? Well, remember this in the box is determined experimentally, this equation. So you do this by setting up charges, measuring their distance, and then you get the constant of proportionality. But later on in electromagnetism, we see that this constant, epsilon 0, is actually really important, and it's given a name. K is not given a name, but this guy is. This is the permittivity of free space. And so it's worth it to break up that constant of proportionality and relate it to epsilon 0. And epsilon 0 is something that you want to get used to early, and we're going to use that often. So we'll often write Coulombs Law with this thing plugged into K there. Now let's represent Coulombs Law with a little picture. Let's say we have a charge, a point charge Q1 here, and we have a point charge Q2 there. And maybe I've got, some separating distance there. In this case, from Q1 to Q2, right? That's R12. So this is the vector R12. Again, I want to emphasize you get your from and to's correctly. Distance vector from Q1 to charge Q2. So we're going this way. That's R12 depicted. And so in the equation here, we've got a unit vector pointing that direction. So a unit vector, depending on the scale of my picture, might look like this. This might be AR12, a unit vector in that direction in green. Also, we usually set up a coordinate system, and I've made no assumptions about where these things are located, where these charges are located, so I'm just going to pick maybe here. There's my origin of my coordinate system, right? And then from the origin, I can talk about, some position vectors. There's the position vector for Q1. And here's the position vector for Q2, right? So we've got the position vectors, and then R is the distance vector. And we talked about these things before. So let's just be concrete. That distance vector is the difference of the distance of the position vectors. And the only thing I haven't shown yet in this figure on the right side of this equation is actually distance. So the distance here, this is R. So R is the length of that distance vector. That makes sense. All right, and then I also want to point out then a unit vector. Remember how we got unit vectors? We took the vector and we divided it by its length. So if we wanted a unit vector in the direction R12, we would take the vector R12 divided by its length. That gives us a unit vector. All right, and after I do that, if I plug in this unit vector into Coulombs Law, then I see that this F12, the force 12 there, is K, Q1, Q2, R12 over R cubed. So this could be a handier way, or a more useful way of using Coulomb's law than its original form, because we're always going to have, we usually know the position of the charges, and then we're going to have to get a unit vector in that direction anyway. So this is how we get the unit vector. So we might as well write Coulomb's law like this. Finally, I want to show in this figure the direction of F12. Notice that if Q1 and Q2 have the same sign, right, then the numerator is and the denominator, because the denominator is a length, this whole thing is positive if Q1, Q2 have the same sign. So that means that F12 is in the direction of R12 if they have the same sign. So, and remember, F12 is the force experienced by Q2. It's the electric force on Q2. That's important. So that's why I'm drawing it over here, on Q2. All right, so I want to show you, before I put, I'm going to put one more vector here, f21, and I want to show you that to get f21, what I would do is exchange the subscripts. K, Q2, Q1 over r squared, the separating distance is still the same, times a unit vector from 2 to 1 now. And what that does to my vector is negates it from its original form, right? From 1 to 2, that would negate it. And then in the numerator, of course, I can switch the Q1 with the Q2 because multiplication commutes, right? So I can just make this K Q1 Q2, bring out the negative. And so what is this thing? Well, that looks much like F12 except for the negative sign. So what we conclude is that the forces, so now this is the force on 1 by 2. The forces are equal and opposite. So I'm just going to draw that on my figure here. This is F21. The forces are equal and opposite. They must be, right? From Newton's third law. For every action force, there's an equal and opposite reaction force. Now, notice that when I drew this figure, we assumed that Q1 and Q2 had the same sign. So in this case, they repel each other. Q1 wants to go to the left in my figure, Q2 wants to go to the right in my figure. Same sign, they repel. If they have different signs, then the vector would flip and they would be attracted to each other. So this is like forces repel, opposite forces attract. The electric force, like any other force, is a vector, right? And multiple forces can combine by adding corresponding components. So this is the superposition principle. So if we had other charges like Q3 and Q4, and we wanted the force on Q1, what we could do is find the force due to Q2, due to Q3, due to Q4, and then do the vector sum of all of those forces. Next, I want to mention what's called the electric field. And to do that, I'm going to erase the figure that I've drawn. Actually, I think we can erase most of this. Let's suppose that we had a charge that was fixed in space. All right, maybe it's a positive charge. Or maybe we had many fixed charges in space. But for simplicity, let's just say we have one. We could ask the question, what force would this charge exert on another charge if it were to be brought close, in the vicinity of this fixed charge? All right? So let's be concrete here. Let me just label this. This is the fixed charge. And I want to know, well, now I have this charge here. Let's call it little q. And I like to call this thing a test charge. I'm going to test the area around my fixed charge, in the immediate vicinity of the fixed charge. I'm going to bring my test charge in the immediate vicinity and see what happens to it. What kind of force does it experience? Now, of course, from Coulombs Law, which I erased unfortunately, but in this case it would be, if this was Q, it would be capital Q lowercase q over r squared times AR 1, 2, like this. The force that this test charge experiences is dependent on how much charge that I'm bringing in. But this is not what I want. I want kind of a normalized version of this answer. You know, I want a normalized version of the force. I want it to be independent of my test charge. I want to just kind of probe the vicinity and not worry about how much charge I'm bringing in. So what we do is we normalize the force the electric force by the test charge. And that is what we call the electric field. So the electric field then, so once we do that normalization, is independent of the test charge. That's the point. That's the purpose here. It's KQ over R squared. And then we just drop the subscripts and we just write a unit vector like this. So now we can forget about the test charge and we can say this is the electric field due to my fixed charge Q. And this is because we normalized it by coulombs. This has units of newtons per coulomb. Newtons per coulomb, force per charge. Force per charge. So if I brought in a test charge that was twice the charge as originally, then it would experience twice the force. Newtons per coulomb, or it turns out that this is the same thing as a volt per meter. And we can describe this electric field due to this fixed charge with some electric field lines. And we'll have more to say about electric field lines later on in the course. But for right now, I can describe this situation by putting some lines that radiate out from the fixed charge and whose arrows decrease in size. So I will explain that in just a little bit. Let me finish making this picture. Okay, so my claim is that these blue lines indicate the electric field due to this fixed charge. And we even might label it E like this. This is an electric field and it's a vector field. The reason they point outward is because if I were to bring my test charge, assumed positive, into the vicinity here, this region in space, the charge would be propelled, you know, because they are like charges, away from the fixed charge. So the test charge would move in the direction of the electric field. That's why it's pointed outward. Also, the arrows decrease in size. And the reason they decrease in size or length from the charge is because the force experienced by the test charge goes down. The force goes down with distance, right? So as I move my test charge away, the force is getting less and less. That is, the electric field gets less and less. And so we show that with smaller arrows. Also notice the concentration or the density of arrows also gets smaller the further away from the test charge I get. Again, because the force experienced by a test charge goes down as 1 over r squared further away. So for example, if I drew a circle here, right, I get 2 arrows in that circle. If I draw the same circle here, further away, I only have 1 arrow, right? And if I draw the same circle here, I have 0 arrows. So the density of arrows is going down the further I get away. So this should then begin to explain the electric force and the electric field. those are two concepts that we've seen in this video. Also, I want to point out that remember that Coulombs law was experimental. It cannot be derived, right? So we know that these like charges attract, and we know that like charges repel and opposite charges attract, but we don't really say what is doing that, what is in between there that's doing that attraction or repulsion. And in many ways, again, I'll say that this is related to gravity. This is similar or analogous to gravity, where we know that the apple falls from the tree and it's due to gravity, and we can describe gravity's properties, but we can't really say like what is in between the apple and the earth, right, as the apple falls. And so what we just do as physicists, as engineers, we say that this is a fundamental force. It cannot be broken down anymore. So that's why Coulomb's law is not broken down any further. That's experimental. It's not derived. Now, this video was on point charges, when we have a charge here and a charge there and a charge there. A more useful application to Coulomb's law is when we have a distribution of charge. We have an object, like a metal rod or a sheet, that is uniformly charged or has some sort of charge distribution across the entire body. And then we can talk about electric fields and electric forces. So that's what's coming up next, this more useful idea, application to Coulomb's law. So I will see you then.